We're finally going to get through the first chapter here. Let's finish up this chapter right here. Right there. Okay, let me just kind of finish this chapter. The last part of this chapter really isn't on MatLab, but it's kind of an interesting session that you might want to steal for any of your classes. And this particular author has introduced something called the steps in engineering problem solving. That's a big one that EAC's been talking about out there. But this is the steps in problem solving right there. Number one thing is understand the problem. Number two, collect the known information. You realize that some of it may later be found to be unnecessary. And I know when I write exam questions, I always put unnecessary information that completely baffles the students. Why, why did I tell them that it's not part of the problem that they're, but again, that's part of problem solving is what information is relative. So determine what information you need to find, simplify it only to contain the required information, state any assumptions you make, draw a sketch that there, and label any necessary variables. In other words, visualize what the problem looks like. They're getting a little cold back there now. That there. Yeah. Okay, you that there. So draw a sketch. Have the students visualize the problem. Determine what the fundamental principles are. Matter of fact, I can probably cool this mine off too. That there. So that there. Think about the solution and consider other approaches. In other words, does your approach make sense? Label each step, understand the purpose. If you're writing a computer program, make sure that you do it by hand, make sure that you have an idea of how you're doing it. That's a big one because I teach, a lot of the courses I teach have computer programming as part of them. And you have to be able to work the problem by hand before you can write a computer program first. And students don't always understand that. Out there. So, there. And check the dimensions and out there. In other words, the famous lunar landing that missed because one set of engineers used metric units, the other set of engineers used English units, and so out there. And reality check. And again, let me just take a second to talk about this one here. Out there. And again, this is not part of MatLab here, but this is a very important step that how many of you have had students that have used a formula that was taught in class that was the wrong formula and got an answer that was completely bizarre, and then they submitted it on a homework assignment or an exam? But you're asking for the current going into a small DC motor, and someone comes back with 3.5 gigaamps right there. You just look at the answer and you go, what's going on? How do you convince students that they have to think about their answer? What is the velocity of a vehicle going down a road under certain conditions, and they come back with 3.5 kilometers per second right there. And I know you've had students do that, right? That there. So this reality check is one of those ones that you want to just slap people with that there. So the precision, simplifying the requirements, interpret the mathematics that there. So again, that there. Sometimes the mathematics gives multiple answers. Sometimes those multiple answers have meaning. That there. And it's just, again, this slide is not part of this class, but I just find this particular set of instructions on how to do problem solving an interesting set of it. That there. There's 100 different versions of this out there, but I've just found that this one's actually a pretty good set right there as you go through that there. And again, if you're developing a computer solution, you have to state the problem, specify what the input is, specify what the output is, and then you have to walk through the solutions by hand with a calculator. Sometimes use simpler data if necessary to make sure that the steps, the relationship there, and then you write and run the program. Notice that if you're out there, and if you're dealing with MATLAB and you're writing a MATLAB script file, this actually has to apply. Now, as you go through and write a MATLAB script file, you may be using, instead of a calculator, you may be walking through the steps using, using the command window and solving the problem by hand, and then you write the script file based on the steps that worked. So almost every script file that I've ever written started off as me sitting down in the command window solving the problem by hand, and then I write the script file afterwards. Right there. So the script file, and the reason I write the script file is so that next time I want to solve the same problem, I just open up the script file and change the variables, and then I can run that there. So again, check that there. Again, that there. And that's it for the first chapter. It only took a day and a half almost to go through one chapter in this book. I gave you 4, so I don't think we're going to get through all 4 chapters right there. So let me go down to chapter 2. And chapter 2 actually, I'll be honest, a lot of what's in chapter 2 has already been covered, and I'm going to skip over that there. So we may get to chapter 3 by the end of the day there. So chapter 2 actually concentrates more on the structure of arrays and cells and some of the linear algebra concepts. So, right there. All right, let's start off with a problem right here. This is a mechanical problem. We have a vector P. A vector P happens to be an array in space. It can be a force. It can be up there. It's specified by 3 units, X, Y, and Z, or Z if you're in the US, X, Y, and Z, right there. And MATLAB can have vectors with more than 3 elements, but typically, if you're dealing with mechanical systems, you're dealing with 3 elements up there. So if you're dealing with electricals, then you can have far more than 3 up there. So, there. So you create a row vector by, and again, these are just the steps. We've already done most of these up there. You can create a row vector by putting a comma or a space in between. The commas are unnecessary. I've done that before. There. You can create a column vector the same way and use the transpose notation right there. Right there. So actually the bracket 3, 7, 9 bracket is actually creating a row vector by putting the little apostrophe here, right here. By putting the little apostrophe there, it converts it to a column vector, or you can put semicolons in between, right there. Either one, right there. The semicolon is used to denote row changes in vectors, right there. Now, one rule of here, now this is just a column or row vector, right there. You can create vectors by appending one vector to another. So you could type, for example, in other words, I could set up a row vector U is equal to 1, 2, 3, 4, close that. V is equal to 5, 6, 7. X is equal to 8, 9, 10, right there. And I tend to forget that equal sign from time to time, right there. And I can say that XV or UVX is equal to UVX, right there. And that creates one large vector with the 3 of them just tacked on each other. Now if I see they're all, see U is 1, 2, 3, 4, I'm going to change U is equal to 1, 2, 3, right there. And the reason I did that is V is X, that there. I can also create a 3 by 3 matrix by putting the three of those in that there and putting a semicolon in there, and I can say X, Y, Z is equal to U semicolon V semicolon X right there, and that now creates a 3 by 3 matrix right there. So by putting the space in between, I concatenated the two rows that there. By putting the semicolon in there, I took one row, the first vector made it the first row, the second vector the second row, and the third vector the third row right there. Now I can do the same thing with column vectors. U is equal to, and I'm going to cheat here, and I'm going to put just an apostrophe there. See, now U is a column vector. V that there is a column vector, and X is also a column vector now, right there. So then I can say X, Y, or UVX is equal to UVX right there. And that does a similar thing now, right there, except for it looks like it's transposed up there. If I want the same thing as I had before, I can put the apostrophe up there. So the apostrophe just takes rows and makes some columns right there. So I can manipulate my vectors in my arrays very simple this way right there. I can append them to each other. I can make them into rows, columns, space, and a space or a comma makes it the next element in the right there. Now if I was to do this and put a semicolon in between right there, that will make it one large column vector right there. So because I'll take the 1, 2, 3 there, and then underneath that in the same in the next row will be 4, 5, or 5, 6, 7. Then the next up there. Now what I can't do is this, because the dimensions are not going to be right there. So as a general rule, all rows have to be the same size and all columns have to be the same size. Now I can have them different. I can have a vector UV is equal to UV right there. And now I have a 3 by 2 matrix right there. And you'll notice that it shows up over here. UV is a 3 by 2 matrix right there. So we can there. So you can come up with any combination of doing rows and columns that there. And that's just simply how we manipulate. And that goes back to what I said before. MatLab stands for what? Matrix Laboratory. So it's designed to manipulate matrices right there. Colon there. Now this particular one is the one that I've been using for my sine example. My starting value, my increment in between, and my ending value. Right there, we've seen that one already, but we can do that one again. X. Well, let's just say T is equal to bracket 0, 1, 20, right there. And it gives me something between 0 and up there. I can change this to a 2, and it'll give me all the even numbers right there. I can change this to a 3 right there. I can change my starting there to -5 right there. So again, all it does is give me right there. If I want that to be a row vector, then I think I can just do that there. Yeah, or a column vector. I just put the that right there. So now in MatLab, that there, yeah, the apostrophe doesn't work that there. And well, in Octave 2, again, the syntax, the brackets are not necessary. That there. So that there, you don't necessarily have to have the brackets, but you can't put the transpose on there unless you have the brackets there. That there. So if you do it without the brackets, right there, it still does this roll. It ignores that apostrophe at the end, right there. And I'm just going through some of the syntax that there creates a vector with spacing that there. So again, that you've seen that many times that there. So there, and again, remember what's going on is in the background. MATLAB actually does a for loop. That there. So there. Linspace is one that I really like because linspace is that there. It gives me the upper lower limits and the number of points. It doesn't give me the spacing. It calculates the spacing for you right there. So linspace is the equivalent right there. So what that does is y is equal to linspace, and I'm going to start at 1 and then comma, and I'm going to go to 20, and I want 10 points right there. So it gives me between 1 and 20, and it will give me 10 points. The spacing it calculates for me, that's there. So it's similar to what I was doing earlier. In other words, I can do x is equal to linspace 0, comma, 2 times pi, comma, 500 points right there. And that created x is now a, where's x right there? X is now 1 by 500. It actually, well, no, it is 5, yeah, it's 500 because I want it to be 500 points. And then y is equal to sine x and plot x comma y right there. And I get the same graph. The only difference is that instead of this command, using the triple command, which is probably that there, so using x is equal to bracket 0 colon 0.1 colon 2 times pi. That I don't know how many points I'm going to get because it's just going to fill up the array. In this particular case, I got 63 points right there. Right there. So again, linspace gives me 500 points and just calculates the spacing in between automatically that there. So that there. If n is left out, then the spacing is set to 1. Okay, yeah. So if you didn't specify the number of points, it will just generate an array, or a row vector using a spacing of 1 right there. So it's just another command that does a similar thing to the previous command. This does one way of doing it right there. Here you're specifying the beginning, the end, and the number of points. The spacing in between. Here you give it the beginning, the end, and the number of points, and the spacing in between is calculated. This one here, we don't know how many points that's going to be. We have no idea how many points that's going to be. Right there. Right there. It will calculate, in this particular case, it's going to be 0, 2, 4, 6, 8. It's going to be 4 points right there. Right there, 6, yes. Or 5, excuse me, I forgot 0 right there. Okay. Log space, log space actually does the there between 10 to the A, and this does a logarithmic right there. So again, this actually develops a log array of logarithmic values between these, between 0.1 and 0.6, and at there, excuse me, at there. The log of -1 is 0, the log of 1 is 0.1, 4 is, excuse me, -1 is going to be 0, this is 0, oh no, 0.1, okay, yeah, 0, yeah, 10 to the -1, yes, 0.1, 0 point, at there. So this just does it in the logarithmic, fact, at there. And for whatever reason, I don't have an example for this, which I should have hundreds of examples, because this is exactly what we use for doing the calculations of filters. We use logarithmic space, but I did not prepare an example with this one here. And since he's a mechanical engineer, he probably doesn't have a good example right there. Because how often do you use logarithmic calculations? Chemist folks I know do it all the time, because you don't count. You look at half-life as a logarithmic function. You don't look at the half-life because it is a logarithmic function, right? The half-life of a drug or a chemical reaction. That there, the decay of uranium. You don't. Yeah, because I know people that do chemical research on drugs. They use logarithmic functions all the time, looking at how long a particular drug is going to remain in your system if its half-life is so long. That they're in pharmacy students will do that a lot. Of course, I put an ex-wife through nursing school, so as we were looking at drug interactions and stuff, she never understood the math involved, but I did. She just knew that you stuck some numbers into a table and into a formula that told you whether it's safe to take a particular drug. I had no idea what that there, but so actually it was back then, it was a long time ago. She used a Palm Pilot and used a program on a Palm Pilot to calculate when it was safe to mix drugs out there. So, but logarithmic spacing, us electricals use it a lot for filters right there. So, mechanicals, I don't think you use it very much right there. So, magnitude, length, and absolute value vectors. Again, this is getting into the magnitude of a vector is the square root of the sum of the squares at there. Same as the vector's geometric length at there. So that's at there. If you're looking at a three-dimensional vector, it's x1 squared or xyz. So it's x squared plus y squared plus z squared, and the square root of all that tells you the length of that particular vector at there. So it's the same as the geometric length. The absolute value is the absolute value of each element. There is no absolute value of a vector per se, but the absolute of the elements of A. So in other words, if x, y, z, if x is 0, 2, 4, and 5, its length is computed by length, its magnitude is calculated here, right there, length of x. Now this length of x is actually the number of units in there. There's 3 units in that there. So you can write a short little program where you can feed it any vector and come back with its magnitude right there. So that's it. And hopefully before the end of the morning we get to functions right there. So the absolute value is just going to remove the negative signs. All that does right there. This is the only negative right there. Matrices. I've already been talking about matrices. Everybody here should have had some matrices in your history. Otherwise, there would be no point in taking a workshop on how to use matrix library, your laboratory, right? So there are special cases of matrices having vectors are a special case right there. So there, again, this shows how you would normally enter a matrix right there. So now you can enter matrices into MatLab. I don't think this works in Octave. That there, again, I showed how you could do that with that earlier. I showed that earlier with the XYZ or UVX. I think I used UVX where I did combine that by putting the semicolon. I've already done that there. And you could even do this here. Right there. Now, normally I just, that's the same, the brackets are not necessary there. Right there. You could just remove those those inner brackets. Now, in a case of a let me see, I want to see something real quick. Oh, wrong. K is equal to 1, 2, 3, semicolon, 4, 5, 6. Nope, that doesn't work. You need to put that in a bracket. Right there. Because you can do K is equal to 1, 2, 3, 4 like that. No, that doesn't work either. You still got to put that in a bracket. Yeah, specifying the arrays, you have to put them in brackets. But you can do, because what he did before is he did the K is equal to 1, 2, 3, 4, bracket, 5, 6, 7, 8, bracket, bracket. And it's looking for another bracket because I forgot to close that bracket off. One, 2, 3, 4, close bracket. 1, 2, 3, 5, 6, 7, 8, close bracket. All right. It does. I'm doing, yeah. Evidently that doesn't work in Octave because yeah, okay. That is the first problem I ran into, is that this does not work in Octave. Right there. That does not work in Octave right there. You have to leave those brackets. You put those inner brackets in Octave, it just looks at you funny. So Octave cannot accept that format right there. It has an issue with that there. So array addressing, again, V represents all rows or columns at there. So again, this is simply saying that, again, this is a vector right there. So when we look at here, we're looking at there. So if I have an array, and I'm just going to say B is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, right there. So so if I say V 3:6, right there, it gives me the third element, the fourth element, the fifth element, and the sixth element in the array. So it gives me, so I could say K is equal to V 3:6 right there. So that creates a new vector K with just those elements, that subset of that vector right there. So, and that works. right there, if it's a row vector or a column vector, right there. So if you wanted to just take part of an array, so for example, I created an array of the average temperature in a month, and I'm going to do this in Minnesota, okay? I'm in Minnesota, and I'm going to create an array. I'm going to call it av temp is equal to, I'm going to start with January. So I'm going to say the average temperature in January is minus 20 degrees. Average temperature in February is minus 15 degrees. In March, it's 0. In April, it's probably 5. In May, it's probably 12. June, it's probably 15. July, it's probably 20. August, it's probably 25. See, now we're August. Next month after August is September. That's probably 20. October, we're getting back down to 15. November, we're probably back down to probably about 12, or we'll say 5. December, we're probably back at minus 10. So there's my average temperature for the state of Minnesota, you know, for each month right there. Well, I want the average temperature for the summer, so the summer is defined by June, July, August, those 3 months right there. So June is the 6th month. So we say average temperature, summer average is equal to average temperature. We should go to 6, and we go 6, 7, 8 right there. Right there. So now we've got the average temperature in the summer in Minnesota. Right there. So now unfortunately winter wraps around, so we can't use winter as our example right there. But again, that allows me to look at these 3 months, what the average temperature is for June, July, and August right there. This gives me the average temperature for the entire year. Right there. That gives me my average temperature for the entire year right there. So December, January, on down. So like I said, December wraps that there, so we can't do that in December right there. Although we can here in a minute. All right. Array addressing at there. Again, that's what we've done before. Denotes all the elements in the third column. Now here we're talking about a matrix, that last one right there. That one there denotes all the elements in the third column of the matrix right there, is what that says. So that's kind of a funky one that there. So A is equal to, I know why I keep not hitting the equal key is I hit the backspace next to it on this keyboard. 1, 2, 3, 4, 5, 6, 8, 9, 10. Right there, there's my matrix. So if I take A colon comma 2, that gives me the second column right there. So I can say A colon comma 3. Yeah, A colon comma 3 gives me the third column. Now if I want the second row, I would say A 2 comma right there. That should, no. Yeah, that's not. Pulling the rows out is not as easy. Right there. Colon denote all the elements in the second through the fifth column. So if I want the second and third columns, I would say, again, this is the columns right there. So again, we can say A, comma, colon, 2, comma, 3, I think that's right. Colon, it's colon. And you can tell all right. Oh. What am I? I'm in MatLab. What am I doing wrong here? A colon. Oh. Yeah. Okay. And this syntax is very, very funky to remember. That there. I rarely do this stuff, as you can guess. And I've seen people that, mathematicians that work with linear algebra problems, say solving, optimization type problems or solving, mapping issues. That it's very common to try to separate certain, create submatrices out of matrices, and that. From an engineering standpoint, I've never done that. There, especially in my signal processing area, which is what I've used this more than anything else. Right? As I said, I was going to fly through these right here. Oh, that there. This is all out there. Okay. And again, here's the actual format that you would do right there. It's the first one, comma, the first, so this is rows 2 and 3, starting with columns 1. So this is right here, and let me just circle. This is taking the second row and the third row right here, and we're going to start with the first column and go to the third column. So this becomes the matrix that we're pulling out right there. So this is the actual formula that you want to look at right here. This is row, beginning row, ending row, comma, beginning column, ending column, right there. And this here, these two here, is kind of a funky thing. This colon means all, right there. And this is going to take from columns 2 and 5. This is rows 2 and 3, columns 1 to 3. Right there. So again, that's how you would subdivide. Again, the easiest syntax, if you remember this one, or remember that you can do it and look it up, that's all you need right there. I have not, again, and I said from the beginning, I am not the person who uses MatLab to its ultimate use to the fullest. That there, for whatever reason, I happen to be the expert here, but there are people that use it a lot more than I do that use it, and I know mathematicians that have used this for different things to subdivide matrices. We typically don't do that out there. Not the type of research I've done, and definitely in none of my classes will I ever use this. That there. I'm going to skip this one. Length, we've already talked about the length that determines the number of elements if it's a vector. or the largest value of M. This is kind of an interesting one. The length here, if it's of a vector, returns either the number of rows if it's the largest, or the number of columns it's the largest. So if I said that M is equal to, and I'm going to say 1, 2, 3, 4, 5, 6, semicolon, 6, 5, 4, 3, 2, 1, semicolon, 0, 1, 2, 3, 4, 3. That's a 3 by 6 matrix. So if I go length M, right there, that returns 6. If I go back here and I put an apostrophe in that there, that now becomes a 6 by 3 matrix. So if I go the length M again, it still returns 6 right there. So that's the, that's the only thing about that particular one right there, the length at there. And max, the algebraic largest element in A is its vector. It returns the row number that contains the largest elements at there. So again, if they're complex, then they're going to at there. So that there. So K equals max A is similar right there. Stores the maximum values in the row vector A and their indexes. Again, I don't worry about them. These things are things that are fairly rare. You're going to use them out there. Row vector containing sizes of that there. Size A right there will return a row vector that gives M at there. So if I go back to size M right there, that returns 6 by 3 right there. So 6 rows, 3 columns. If I change M to that there, and I do the size, it's now a 3 by 6 right there. So it just returns the sizes. Now, these sizes do come into play for some operations. If you're programming and you have a matrix, you're not sure how big it's going to be, and you want to do operations on that there. So you want to take the average of each column and create a row vector of that there. So you need to know how many columns there are and how many rows. And you'll use those as your counters for your for next loops, for your for loops. I don't have time to go through that there. It'd take 20 minutes to go through the programming example. But what I'm saying is that there, and maybe my battery is completely dead. Right there. I actually ordered batteries last night. I ordered 4 of them now. They seem to last about 6 months to a year, so that'll get me through my retirement. 4 new batteries. Right there. So if I got a row 1, 2, 3, 4, 5, 6, 5, 3, 2, 1, 8, 9, 7, 8, 4, 2. And I'm just writing numbers down. Right there. This happens to be a matrix that there. And this matrix could be one that somebody's entered. I could have read it from a file. I could have got this matrix from anywhere. But once I have this matrix there, I want to create another vector that's the sum of each of these rows right there. I want to sum those up right there. I might want to put another one here where I have the average set there. But I want to analyze this matrix set there so I can use that size to determine that this is a 4 by 5 matrix right there. So then I can do a 4, 1, colon, 1, colon, and I'm going to call size, well, actually, I'm going to call it S, and I'm going to say 0, 1. That's the number of rows, and then down here I could say 4. And I'm going to say X equal 1 colon 1 colon, and I'm going to say M or whatever, and that's the number of columns right there. So I calculate the columns right there. So actually, I could just use S2 here, right there. So going back to this right here, is that I can then say S is equal to size M, right there, and then I can say S1 is 3, S2 is 6 right there. So I can get the number of rows and columns, I can use them for indexes on my for next loop right there, or my ending values on my for next loops right there. So it's usable for programming to be able to tell the size of the matrix. It's not obvious at first what it's valuable for, but if you're writing a script file where you're analyzing the contents of a matrix and you don't know what the size is, then that there. So, okay. Then we can there sums the elements of each row, each column, each row. You retain each of the elements in each column in an array, so that there it returns a row. So again, I had here M right there, and I could do sum 1 is equal to sum M right there. And that returns a row vector that there is the sum of all of column 1, sum of column 2, sum that there. So if I look at 6 plus 1 plus 3, that's 10. 5 plus 2 plus 6, or 5 plus 2 plus 4 is 11. So what this right here is, this is the sum of this column, sum of this column, sum of this column. So again, I was just talking about if you wanted to write a program to do that there. So if I wanted to find the average that there, I can say average 1 is equal to sum M right there, and then divide by right there, and I'm going to say 3 in this particular case. You would actually have to find we already got S, so S1 right there. So that gives me the averages of the rows right there. But I'm using here, so 1 plus 6 plus 0 is 7 divided by 3. 2 plus 5 plus 1 is 8 divided by 3. 2 plus 3 plus 4 is 9 divided by 3 is 3. So again, what I'm using right there is I'm using the sum along with the size to calculate the average of each row right there. So, as you're doing non-engineering type math, for example, you want to add up you can do that fairly easily using these out there. So it's kind of a way of looking at these functions, looking at the array, what use is it, but they've got plenty of uses there. Okay. There, and again, this goes through and use some examples, workspace browser, got there. Now, one of the things we could do is over here, let me find M here. Now this does not work with Octave, but I can double click here on M right here, and it should open up, and there it is, a Excel type spreadsheet, and I can edit the array here. And a lot of times if you're working in the workspace, it's a lot easier to add it there than to try to remember the, where the colons and the commas go. So I could generate a new array right there easily enough. But there, as a matter of fact, I can come over here to workspace right here. Actually, no, you have to create the variable first, but I can say L is equal to 1 right there. And I create the value, the variable there right there. And then once it's created, I can just bring it in here, and then I can put whatever I want in that. 1, 2, 3, 4, 5. I don't know why I got 6. Now, notice as soon as I go up here and I put a single value in there, notice that everything under that now fills in with zeros right there. Same thing over here. If I put in another row here, there it fills in there. Because if I don't put something in there, the matrix won't be a legit matrix. So all the rows have to be the same. So, and then I can just go through here and of course, as you can well guess, I'm just putting in and then I can close this right here. Close that right there. And L is now this matrix right here. So I've set up L by using the spreadsheet. I personally find the spreadsheet a lot easier to put in large matrices. Right there. Now the other thing here is I'm going to go off the sidetrack here. If we had and I'm not sure if this is going to come up with a legit, I'm just going to make up some numbers and put in here. Well, let's say I'm going to bring L up here again, right here. And I'm just going to delete that. Delete the rows. Don't zero them out. You have to delete them. But I could put a complex number in here, 3 plus 2i, 4 minus 3i, 5 plus 5i, 2 plus, now again, I'm just making numbers up, so 1i. I'll leave that one, that there. 5 minus 36i plus 2i, 3i, right there. So I close that there. Now if I do L, right there, it shows as my three-dimensional complex array. I can do another vector in here. B is equal to, and I'm going to say 10, 12, and I'm going to say 0, 32i right there. So there's my, right there. So what I've done there is I've gone through and I represented a system of equations right there, where again I made these numbers up so they're not going to make any sense. Right there. Right there. Okay, well, let me, right there. In other words, L is equal to this matrix right here. And this matrix might come from a circuit right there. So this is my impedance right there. My impedance is in a 3-loop equation right there. Now again, this doesn't represent a real circuit because I didn't, I didn't draw it from a circuit that there. V is equal to my voltages, and this is like that resistive circuit I did yesterday right there. Only now these are capacitors, inductives, and they're complex. And any of you that remember your freshman electrical engineering course, solving a 3x3 mesh problem with resistors only was a pain in the neck, right? How many ever had to do that with complex numbers? Right there. So we can go through here and we could say then I is equal to L raised to the -1 times V right there, and that would be my solution right there. So it's just as easy to solve complex numbers as matrix problems as it is real numbers right there. And the only thing is that I hate adding complex numbers without using the spreadsheet. It's so much easier to look at that spreadsheet and look at my equations that there, and then trying to say that L is equal to, and that there, right there. And I'm just going to put 1 plus 3i space 2 minus 4i space j, and just go on and on. You can see how that's time consuming versus just going over here and double clicking there. And the other issue is that it's easier to see what you typed there, in terms of what the matrix looks like. So I really like using the spreadsheet to enter the matrices, especially if they're a large matrix, right there. So that there. So okay, where are we at time? That there. Right there. Okay, that's the array editor. Right there. Concatenate, just simply two-dimensional arrays are layered to produce that there. This creates a very interesting situation, is that this is actually concatenating along a new dimension right there. So you've got pages. It's now a 3-dimensional array. So I've got 2 dimensions, and now I've added a 3rd dimension right there. So it's used, and mechanicals, you probably use it more than we do. Programming classes, I always look at it as I have a 2-dimensional array for the temperature each day of the week, or each day of the week, and the 2nd dimension is each hour, and then I can have a 3rd page for each month, and a 4th dimension for each year. So you can add more and more complex arrays that there. So you would have a page for each one that there, or a book. It gets messy, but you can have 3-dimensional arrays, 4-dimensional arrays, right there. So it creates a new array by concatenating arrays and along dimension n. So you get dimension n would be 3rd dimension, 4th dimension, 5th dimension, right there. So, okay, here's a little that there. This is an example right here where you want to add 2 vectors, vectors r and vector v. Right there, those are each 2-dimensional arrays, right there, or 2-dimensional vectors, and we just simply add the 2 together, right there. So, if we want to add arrays, it's element by element. If we want to add vectors, it's vector by vector, right there. So right there, we just simply add the arrays, and it works perfectly fine. And I'm just kind of rushing through just to get through this here. I'm not taking a lot of time right there. If we want to subtract, the same thing right there. Right there, so we can add A plus B and A minus B right there. Now, when you do the subtraction, these arrays have to be the same size. It doesn't make sense to subtract a three-dimensional array from a two-dimensional array right there. If you have to do that, then you probably need to create a third array of the smaller size and then concatenate it back. You can do it, but it's a pain. Simple addition, they have to be the same size right there. If you want to multiply two vectors together, right there, or scalar multiplication, all you do is just multiply it right there. So scalar multiplication is right there. An array B1 is equal to 1, 3, right there. B2 is equal to 3 times V1, right there. And it just multiplies each one by 3, right there. So a scalar, and if I have the array, here's M. Here's my large array there. And I can say M2 is equal to 5 times M, right there. And M is 160, 5 that there. I just multiply each element by that there. So fairly straightforward, right there. Right there. So again, B is equal to 2R, so we multiply each one by 2, right there. Multiplying by a scalar does the same thing. Right there, I just did that there. Now, there's two types of multiplication. This is a tricky one because the syntax is ugly. That there. Array multiplication, that there, and matrix. Array multiplication and matrix multiplication. Array multiplication, we're doing an element by element multiplication right there. Matrix multiplication, we're doing a row by column multiplication. First row, first column. First row, second column. First row, third column. Second row, first column. Out there. So we can multiply matrices that way there. I'm not going to go into great detail. Those of you that know that do matrix multiplication understand how it works. I've done a lot of matrix multiplication because we do. I've done that there. So, and I've done a lot of graphic stuff that there where I've had to set up vectors and points. That there where I've done vector multiplication as well. That there. So again, division explanation must be carefully defined when dealing with operations that there. You got the element by element and then the matrix operation. And division and explanation must be carefully when dealing with operations between two arrays. That's a really tough, that's more of an advanced topic. It's probably one I'm going to skip over fairly quickly right there. So here's our element by element operations. And you'll notice that when we got add, subtract right there, and these are with scalars right there. So this is A plus B, and B is a number, then we're going to add 6 plus 2 and then 3 plus 2. A minus B, again, B is a number, 8 minus 5 is 3, 3 minus 5 is negative 2, right there. Array addition is element by element. So 6, 5, and 4, 8 is 6 plus 4 is going to be 10, 5 plus 8 is 13. So we're just adding each element right there. Now that's a vector, but it's the same if it's an array. If it's a two element array right there. Same thing here. 6 minus 4 is 2, 5 minus 8 is negative 3, right there. Now, if you've got the dot before the multiplication sign, That's telling us that this is a element by element. The dot is the key. That there. As I said, the syntax is ugly because you remember, all right, I want to do element by element multiplication. What's the syntax for that? That dot, you'll never remember the dot. You don't do this enough to remember that dot. Now, since I pointed out that you won't remember it, maybe a couple of you might remember it, but it's the dot. And then you'll see that dot in front of all of these right there. So, A dot star B is 3 times 4, 12, 5 times 8 is 40 right there. This is normal division. 2 divided by 4 is going to be right here, and it's not going to say 2 divided by 4, it's going to be 0.5 right there, and it's going to be 0.6 something right there. You know, it won't show that there, so in other words, A is equal to, and they're using 2.5, right? No, yeah, 2.5 and 4.8, 2.5. 2.5, B is equal to 4.8, right there. So it's A dot divide B, right there. So if I do A divide by B, and I doubt if this will work. Oh, it did work. Right there. A times B. That one didn't work. Okay. You know, the dimensions just happen to work out. That there. So again, that there, and I don't do that right. That, you know, I don't, that left division, he uses that a lot. Does anybody use that left division notation? You know, 4, 8. That there. It's actually the same thing as 1 over 4 divided by 8. Right there. It's the same thing that there. It's actually the reciprocal is what it is. I just never use it that there. Because it's not used in any of the math books or any of the formula books that there. But it happens to work okay in the matrix that there. Exponentials, again, we do it exponential by exponential right there. So that there. So when we look at this exponential right there, this one's fairly easy when we look at that there. These are the element by element that there. And again, that there, element by element is defined only that there. So again, they have to be the exact same size that there. Arrays having the same size definition, product that there. So again, that goes back to what I was saying. Okay, column vectors, star dot. Again, we're that there, and we could do one as a transpose as well. That there. So we end up with a column vector right there. Now, okay, this is still column vectors right there. Right there. The square root again is a vectorized functions. It's going to do it by element by element. The square root is an element by element. Right there. And a lot of functions are, like a sine we said was what was that there. So again, when we look at M and we take square root M, that gives me the square root of each element is what that's giving me right there. So, and same thing as if I did sine M, that gives me the sine of every element, each element that there. Because we use that function right there, that sine function, when we did the x is equal to see here we're doing a function we're doing a function call on it, and we're passing an array vector. So it's doing an element by element function on that there. So we've already done that there. Okay, again, this is an interesting one. You could do this one really quick. What he's doing is here we're going to calculate z is equal to the e to the y times sine x times cosine squared x. Right there. Now, we have two arrays, x and y, and we want this to do that for every pair of x and y in the equation. Right there. So, for this to happen, and it can be done, it's not a problem, we can do the exponent of y times star, because that's going to, because when we take y and we find the x, we take y, x to the y, or e to the y, and y is an array, we're doing an element by element analysis of e to the y, right there. So, at this point, y is an array, right there. Y is an array, and as soon as we do z sine x, that is also an array because x is an array. So we want to do a element by element multiplication right there. Then we also want to do a element multiplication here because this is an array. Cosine x is an array. So our multiplications have to be the dot star. Out there. And I've seen, I've actually assigned problems similar to this there, and so many people forget the dot star that there. That there. Because all three of these are arrays and we're multiplying them together right there. E to the y times sine x, this is an array times an array. And then this is an array times the result of this. So the result of this multiplication and this multiplication is also an array. The result of this is an array. Now, as it turns out, they're not arrays, they're vectors. They're vectors out there. So this will work, but we also have to keep in mind is that x and y have to be exactly the same size of vectors, otherwise it won't work, because for every value of x, there has to be a value of y. So we can't have 10 values of x and 12 values of y. It's not smart to stick zeros in there. If you want to stick zeros in, you have to create an array and stick the zeros in yourself. The arrays have to be the same size, right there, or you'll get an error message. So we've got three vectors in this case. We've got x and we've got y. And then our output is going to be z. So we're going to calculate a value of z for x1 and y1. Then we're going to calculate a value of z for x2, y2. And we're going to go through that for all 10 values, 20 values, 1,000 values, right there. It doesn't matter how many values that there. And this is how you would plot a complex function. I have no idea what the result of what this is going to look like that there, but I could calculate this from 0 to 5, for example, right there, and I could plot this function right there. So if I wanted to plot this function right here, for a range, and this is how you do it, and this is probably a good place to end this discussion for the morning, is if we want to plot this function here, and I need something to write on here. Because the problem I've got is z is equal to e to the y sine x times cosine squared x, right? And that's exp. So if I want to plot this, and I'm going to plot this from 0 to 5, right there. So I'm going to say that there, and again, that there, I'm going to say that there, and actually I'm going to have two values that I need to do there. I'm just going to make up numbers here. I'm going to say that x is equal to, and I'm going to say lin space right there. And the reason I'm using lin space is because I want to make sure they have the same number right there. So, and I'm going to go 0 to 5, and we're going to say 100 points right there. And I'm going to say y is equal to lin space, and I'm going to say 1 to 4, 100 points right there. Now the reason I did x and y separately, that there, and again, all I'm going to do is plot this with respect to x, that there. You know, we'll assume that there, but I just want to do a plot right there. And this just happens to have two variables that there. So then I'm going to say z is equal to, you know, let's make sure we get this from there. exp, or right there, and yeah, expy dot star right there times the sine, is that sine x? Right there, dot star cosine, and this was what, x right there, squared, oh, and a square matrix. That is it's telling me that I also need to do the dot in front of that there. Okay. So then I can just do a plot x, z right there, and there's my function with respect to x. And I can also do plot x, z, comma, y, z right there, and I can see the values of with respect to so I can see both of them that there. So again, this is x in the blue, and this is y in the orange right there. So so I'm actually plotting. Again, I have no idea what the meaning of this equation is. I'm just showing that I can plot it with respect to x and y right there. Right there. But that's how you would plot any expression right there, is if you look at these three lines right there, just get everyone's attention right here. If you look at these three lines right there, the first thing I did, well, actually, that there, we also need to have all right. Look at these four lines. That there. What I've done in these four lines is I set x is equal to as an array, and I use the lin space function instead of the starting ending point and the or starting point increment and the ending point. I use the starting point, ending point, and the number of points in between And the reason I did that is because this would not work unless X and Y were both exactly 100 elements right there. Then I set X and Y in the ranges that I want to do that. Again, I don't know what this function is. Normally your function Y, you're doing a function of Y with respect to one variable. Here I'm doing it with respect to two variables right there. Then I'm calculating X by just sticking it in my formula right there. Right there. And then I'm going to plot X versus Y, X versus Z, and Z that they're actually, that's probably, yeah, X along the X-axis and Y across the Y-axis, and then Y across the Y-axis. That's why it's confusing that there. And then Z across the Y-axis. That there. So, and I end up with two graphs shown there. And I haven't labeled the graphs and put any kind of key in that there. Hopefully this afternoon I may jump that there. So, right there. Array division at there. Again, that does similar. That's element by element at there. Array enables the powers, the array scalars and arrays to array powers. This is an interesting one here. By again, we're doing each element one at a time. This is at there. Again, scalar powers. Now we can also do vectors. I think we'll come back after lunch and get into array multiplications at there. I'm going to go very quickly through that there. And I am not going to get into structures with this class. I will not get into structures with this class. Okay, everyone go ahead with a lunch. I want to spend about a couple minutes looking at what I want to do this afternoon, okay? Because I want to jump ahead and just cover some topics. We've only got about an hour and a half, 2 hours of lecture left, so I got to make sure that I cover a couple of things out there. So I want to find the slides and make sure I get them covered out there. Yeah, okay, this is what I want to do. I want to make sure I cover functions. That's Oh,